Hey guys, we are continuing. I got several questions, so I just want to clarify maybe one or two things. The first is maybe discarding is not the right word there, although we do discard these regions. What we really do is quickly classifying them. We quickly classify them as unsafe. So now my whole region here that's separate by this hyperplane is definitely unsafe. So I don't need to think about it anymore. And that's the great thing about that, number one. Number two is, what do I do with the region inside here? So similar to convex relaxation, there is the convex restriction. It's a very new approach. I have only seen one paper, to be honest. We know these people relatively well, and we have been in touch with them. We tried to implement their approach. It didn't work as well for now. But it's an open problem. So the idea is that then I can take a random sample here, and I can create the largest convex region inside the feasible region. Then I can quickly classify inside points as safe. Okay. Now, the major question is what happens with this region here? Because now also, yeah, because for that we haven't done anything yet. And the idea is we do what we have called directed walks, is nothing else than a kind of a gradient descent. So the idea is that we traverse fast through the safe and unsafe spaces and try to focus around the security boundary. And when you use small signal stability, then you have this damping ratio that's a continuous metric telling you how close you are to the security boundary.
Excuse me,
yeah,
sorry. Can you go back to the last? Yeah, so this non-convex stable region, is it the one that you said it's a conservative operating region? No, it's the entire
the region. This is only for steady-state equilibria,
okay.
Right? And the operators may be somewhere. So then you have to have the stability criteria that's somewhere inside here, right? And the operator might be in a very small region in there. So I'm not going to go into more detail into that. I mean, it's parallelizable and variable step size. Just some results. So for the 14-pass system, we're able to, through brute force, we're able to generate the whole space, right? To generate data points with 1 or 2.5 megawatt increments for the whole space. We need about 10 hours. These 5 generators, okay? With the important sampling that for us, at least the time that we submitted that was the most advanced method, it took 37 minutes to generate all possible points. What we are measuring here is how many points we have close to the security boundary. So in this high information content region around the safe and unsafe, because that's what we think is important to map the whole security boundary. And with our methods, about 3.8 minutes, this is like 10 times faster. If we go to a 162-bus system, it's impossible to generate, to assess for all possible operating points, if they are safe or unsafe. The important sampling gets 900 points in 35.7 hours. The approach that we used, or we propose anyway, it gets many more in about similar time. The convex relaxation helps a lot to that. We discard all the space that the important sampling is just spending time classifying as unsafe. Because think that the unsafe region is much bigger than the safe one, right? So if we discard this, then we can be much better. And it seems also that these types of databases have better accuracy when we use neural networks or decision trees. I mean, here we have used decision tree. So better quality data gives better performance as well. Good. Takeaway number 6. So what we need to remember from here is that, first of all, it's extremely complex to generate databases of large, realistic systems. And it's also still, at least for me, an open interest topic, how this database should look like and how we can generate this kind of data fast. If we want to use data-driven approaches for this kind of systems at least, we need to find methods to generate high-quality data. And maybe for load forecasting or for other applications, the data is already there. It's a historical data, and that's what we need. But for this kind of applications, we need to somehow generate it. Okay. Questions? My goal is that by the end of this hour, I'm going to go through 2 or 3 more concepts, 3 actually, and then you have some time to check the hands-on exercise. So one more thing we can do with data-driven machine learning methods is to convert them to mixed integer programs. because we think that this actually has a lot of advantages. To be honest, I was at the Informs conference in Seattle in October. We're going to discuss about decision trees to mixed integer. We do now develop an approach with neural networks to mixed integer. We're not the only ones. It seems that TensorFlow and Google are working on this, and they might have something out in the next couple of months that they convert the information encoded in a neural network to a MILP. Okay, we're going to discuss here about decision trees to a MILP because at least this paper is out, and we haven't. And there is a lot of work about verification. We're going to talk by the end of this hour. So here's what happens. This is the feasible region, and actually the true feasible region of a power system is characterized not only by the steady-state equations, but also by the dynamic stability, right? Which means differential equations saying if something is stable or not. So it's very difficult, actually it's almost impossible, I would say. It is impossible to add differential equations in optimization problem without any proxies. Okay. So there are ideas of how you can have a transient stability constraint OPF or a small signal stability constraint OPF. All of them use some kind of proxies to get the estimate of the region. We're also talking here, in a way, decision trees will also be a proxy for us, but we think that it can be more accurate than others. So here's what happens. Electricity markets already do that. So they try to have linear approximations. That's in Europe. They try to have linear approximations in order to make sure that the electricity market is always operating inside the feasible space. How this is characterized, the stable operating space. Okay. This used to be net transfer capacity. Now it's a flow-based market coupling, which is a bit better approximation. The idea is how can actually capture the whole feasible region. And what we do here, the main idea is the following. We have our database. We train a decision tree that tells us what is stable and what's unstable. And then we convert this information of the decision tree, which remember it's an if-then statement, to conditional rules, which is like a binary and a linear constraint. And this is how this looks like. So if we have done a good job training our decision tree, this is an exact reformulation. So whatever information our decision tree has is now encoded in our constraints, which are linear constraints with binaries. So this decision tree can tell us, for example, that this is stable, which means that it has encoded already the small signal stability and what else this database includes. And now this is reflected in our inequality constraints. This is how this works. So in essence, or essentially what the decision tree does is splitting the stable region into smaller convex regions and assigns a leaf node into each of those. And now this is more for Europe, but this is a flow-based market coupling is actually corresponding to the largest convex region. With the decision tree and the integer variables, we can actually get the other convex subspaces. And again, I'm talking about Europe, but the market algorithm in Europe, it has already integers in its implementation for all the block offers. So this is not something that all. So they already solve a MILP. So some results. The largest convex region covers the 78% of the true feasible space. With this kind of decision tree and then exact reformulation to a MILP, to a mixed integer actually, we can get 22% of the convex space, and the true optimal is actually here, while in the previous case we would only be limited somewhere there. Any questions?
So can you go back to the previous slide?
Absolutely.
So what was that, the optimal boundary? So what respect is that optimal?
In terms of costs.
Cost of
Yes.
And where does it relate to the chart in the top right of it all?
Where does it relate, you mean?
So this is a representation of the other stable, unstable region, right?
So all the green ones are stable regions. So first of all, you must think that this is a projection in 2D, right?
Yeah.
This is a multidimensional space. All the green ones are stable. So this is just a part of the largest stable region that we see there in red, but this is the largest convex region that is stable.
Yeah.
The market algorithm will only focus on this to find a solution, will not move outside that. Is that clear? Or?
That's clear.
Okay.
Can you just go back to the previous slide, sorry?
Yeah.
Yeah, so on that slide, where's the black dot? Where's that represented on the bottom right blob, if at all? Is it?
This is an artistic impression of that.
All right.
Yeah.
What's the system for this? Is it a 3-bus system?
This is 14 bus.
14 bus.
Yes. This is angle difference, can be also line flows. It's the same thing. For a DCOPF, the same thing.
Sorry, I'm a bit dumb. Can you just explain how you came about with the blue box?
This blue or this blue?
The blue box, is that?
This is just one. So maybe it's better. So here, right?
Oh,
So-
okay. It's one of yeah. Okay,
Yeah,
I
it's
got you.
another convex region.
Ah, okay.
So we let's say partition the non-convex stable region to a set of convex spaces.
Sure.
Subspaces. Yeah. So these are several convex subspaces that are not included in the largest convex space. And it's clear here also you can see that it's non-convex. Right? Any questions? I'm moving on. Two more concepts. Now we're going to talk about neural network verification. Okay. To be honest, this also draws from the conversion of a neural network to a MILP. And I think that's one of the nice things for these methods, to be honest. So just as a short reminder, if the time before lunch seems too far away, why do we do neural network verification? If we want to apply them in safety critical systems, it is crucial that we somehow provide guarantees about the performance, if we want to apply them in safety critical operations. Okay? So as we have seen today, up to now, the only way to do that was to get a test database. These are samples, this is statistics, and assess the performance. Can this be accuracy, specificity, recall, or whatever of the metrics you want? This is all statistical metrics. Okay? You must have a good enough database, and then you assess the performance of your machine learning method based on that test database. And then you actually pray that in reality nothing else will happen. Okay? Now, challenge number one, there's no way to guarantee what the output is for a continuous range of inputs. Up to now with the test database, we can assess the performance based on discrete samples, but we could never tell what happens between one sample and the other. Neural network verification can actually guarantee for continuous ranges of data. Okay, number one. Number two, as we said, the test database determines the performance of the network. With the verification, we move away from the need of a high-quality test database. Number three, have you seen that before? First time? So, neural networks or machine learning is applied a lot on image processing. So there is a lot of research around that, and a lot of research with applications on images. So we have an image of a panda, and then we add a very small noise, and we get a gibbon. Is anybody that doesn't know what a gibbon is? Yeah, me neither, I didn't know. So this is a gibbon. Okay. So with a naked eye, something completely different, right? And that's but because I have looked at this picture for a couple of times, so maybe the eyes or something, I don't know. The neural network thinks that it sees a gibbon here. So
Don't try to understand how the neural
yeah,
network
probably.
You can take random dots all over the place and interpret numbers from that. So don't try to understand.
So up to now, if we wanted to identify this, as you also said, so random, right? We just need to be lucky enough to get that this noise will give us this adversarial example. There's no way to systematically identify these kind of examples that are very important for critical applications. So these are the three challenges that actually neural network verification can address in a good way. So how do we do that? The first is we convert the neural network to a set of linear equations with binaries, and I'm going to discuss how we do it. And in that way, actually, the neural network can be included in a mixed integer linear program. The next step is we actually formulate a mixed integer. I'm going to call that MILP, right? I hope everybody is fine with that. MILP stands for mixed integer linear program. If we solve the MILP to zero duality gap, which means that we have found the global optimum, that's what it means, then we get a certificate for the behavior of the neural network. And then the last step is actually to assess if the output of the neural network complies with what the ground truth is. And we're now actually in the process of developing a method that can integrate these two steps into one and have a training process with a certificate. But this is for another, maybe next year. So we have two types of optimization problem that we formulate. Over the past 2 or 3 years, there is a lot. This started, I think, about 3 years ago, almost 2.5 maybe, the verification. and it has exploded in the machine learning community. And what happens here is that we take these methods, we adapt them for now, and we apply them in our problems. The next step is, of course, to make contributions also in the machine learning field. But for now, what this does is it brings some of those insights into problems that we have in parsers. Okay, two types of problems. The first is that we certify that in a region around a reference point, the neural network maintains the same classification. Okay. So then I can certify that for large chunks of my input region, I have the same classification. And that's how I can certify the output for continuous ranges. The second optimization problem we are going to formulate is that we find the minimum distance from the reference point that the classification changes. And I'm going to explain why this helps us systematically identify adversarial examples. Okay, so first of all, the conversion to a millip. These approaches apply to neural networks that have ReLU as the activation function. ReLU stands for rectifier linear unit. ReLU is the most common activation function used for deep learning at the moment. There are other activation functions. In my undergrad, when I took a course on neural networks, we were learning about the sigmoid function. Okay, and probably maybe that was very popular then. I have sat down with a mathematician trying to figure out if we can get the sigmoid into a exact convex transformation. It's impossible. But I think there's a paper now that does some kind of approximation. So what I'm trying to say is that what we're going to discuss here is for the ReLUs, but the ReLU is also the most common nonlinear activation function. So again, what we do is a binary telling us if it's negative or positive, and then if it's negative, this is 0. If it's positive, it's the same as the input. So if you just look online, ReLU is a max operator. It's straightforward to transform a max operator to a binary with linear constraints. So this is, and then all the rest is linear. So these are all linear weights, right? So the only nonlinearity was here, and we found a way to reformulate it. So now we have all the information encoded in a neural network. We have it in the linear equations with binaries. One more thing before going to the actual formulation of the problems, the outputs. Okay, as I said, we have this one-hot encoding. So we have an element, a vector with two elements. If y1 is larger than y2, it's safe. If y2 is larger than y1, it's unsafe. Okay, that's what I need you to remember for the next slide. First, definition of a problem. So imagine now we start with some sampling. That's what we always do. We start with the one sample, let's say the reference point here, that happens to be safe. So this is an actual example that we have in our paper. I think it's a 9-bus system, if I'm correct. So this is the safe space, this is the unsafe, the blue, and the red is the misclassified point. Okay. So we get a reference point that is classified safe, and what we want to do is to find if there is any unsafe classification within a region epsilon around that point. Okay. So since this is safe, y1 is larger than y2. Okay. If I maximize y2 minus y1, as soon as this becomes positive, this means that we change classification. If this remains negative, this means that this gets the same classification for the whole region. So as long as this remains negative, this means that I can certify that all this region around epsilon from my reference point is going to have the same classification. Is that clear? Now, it's up to you to define epsilon. We have tried with different epsilon. Of course, the closer you are to the security boundary, so here you see that we took a smaller epsilon, right? We have to adjust epsilon in order to get the certificate that everything has the same classification. Questions? Yeah.
The square region is just a representation, or you indeed use squared regions? Infinity norm. Okay.
You can also use other types.
Yeah, you briefly discussed on the paper about other norms. Like, did you try with circular region?
The two norm?
Yes.
We could, but then it becomes a secondary cone problem. And
Okay.
well, this remains linear.
Okay. Thank you.
Okay. Next formulation, for adversarial examples. Have you seen that example before? So this is more about safety critical systems. Okay. This is about autonomous driving, which is a critical system. So what happens here is I have my camera on my vehicle. It's driving alone, right? And actually, it understands if there's a green traffic light or a red traffic light. So here it sees that the neural network runs and sees that there's a green traffic light, right? And then I change one pixel here, and now the neural network thinks that I have a red one, so I have to stop. So imagine this happening in reality, the risk for the safety. So we really need to find or identify all those examples and make sure or retrain the neural network so that these examples do not occur, right? And this verification actually gives us a systematic way to identify this example. So how do we do it? Here we actually minimize. So again, imagine that we have, again, we take a point right here. This, I will, yeah, or maybe let me explain that now. Again, the same system, 9 bus. What we see here is in two dimensions, all the red dots are the actual unsafe points, or the green dots are the actual safe points. Okay, the circles around, if it's green, means that the neural network predicts that it's going to be safe. If it's red, the neural network predicts it's going to be unsafe. So if it's green, green, or red, red, this is what we want. The problem is here that is actually safe, but my neural network predicts that as unsafe. We take, again, a random sample, somewhere here that is safe, right? So what I'm trying now to figure out is find me the minimum distance to which my classification changes. So if I am here and the minimum distance where classification changes is there, this means either that there is the security boundary or it's an adversarial example because it's right in the middle of a safe region. So this is the way that we actually check for adversarial examples. Now, here in a very small epsilon, with an epsilon of about 1%, the classification changes. You can think of that as a test database. Okay, this is a test database. We have taken, let's say, uniform samples across the whole region. You can also say that this is actually pretty dense, right? Still, with this method, we identify that very small, in a very small distance from here, the neural network will change the classification. Now, one can say, and actually that's what I say, this is very close to the security boundary. So when you go so close to the security boundary, you can never be so robust anyway. But we tried to find adversarial examples in the, let's say, so impressive as this one, because this is impressive, right? But it was not easy. So this means also that maybe the neural network did a good job here classifying safe or unsafe. But by definition, this is an adversarial example. Questions? Yeah.
I guess I wonder if there is any hope, more hope in the power systems, because actually there is a very clear physical system underlying, while the counterexamples that you're giving there are all images where there's a true non-model case, right?
I agree. Yes, and this can be a really good, really good intuition why this works better here. Yes.
Can you comment on the neural network itself broadly, as because I did understand that neural networks have a tendency to overfit the model, and that could be an example of that. That it couldn't handle something that was outside of what it had seen before. Yeah.
So in terms of accuracy, or that's a good comment. Yeah. I'm not. We have.
So maybe just take it as a comment. Neural networks tend to overfit, and that if you've got something that's really outside the bounds of what it's seen before, it doesn't know what to do.
Yes, yes, great. And actually, that's a nice comment, because what we have to do here is probably retrain, right, and complement our training database with data, so that
new data.
Yes.
To solve conscious of the overfitting problem, is just exposing it to new data.
Yes.
Yeah.
Yes. Exactly. Yeah.
So,
yeah.
But there's like other topologies that they have a feedback system in the neural network, so they may solve this issue. Am I right?
Yeah.
So like with the feedback system, we can.
They
solve
can
this
always.
issue.
Yeah.
Like the RNN, the recurrent neural network. Yeah. Yeah.
But then I think the recurrence cannot be converted to this kind of MILPs for verification. I have the impression. I'm not sure, but that's my impression.
How do you choose the X reference from where you're going to define the
sampling?
Does it make a difference, or
it makes a difference how fast you're going to find an adversarial example, right? But you have to start sampling, and you have to cover the region. So you can even start. So the thing is that this is going to give you the minimum epsilon, which means that if there's no adversarial example, so you pick a point here, and all these are classified correctly, or the same classification, then the maximum epsilon will be somewhere up to here, right? So you can very easily classify, you can very easily say that there are no adversarial examples in those regions, because you have to find the minimum epsilon that you change the classification.
Yeah, and here I come back to the question that
I did outside.
in the morning. Why do you choose to find the minimum epsilon to which it changes instead of finding the maximum to which it doesn't change?
So how can you formulate that in an optimization problem? Because it's easy, it's straightforward for me to identify that as the minimum that changes, but how can I formulate an optimization problem that say, you know what, you must always find the maximum that, if you find the maximum that doesn't change, I can go the other direction, that it won't change, but from this I might already be inside the unsafe region, right?
So in OPF, you can mix a few techniques and get a more accurate result. Has it been is it possible to use two techniques, let's say, to cross-check the references?
Is it possible to use a few techniques to check?
I mean, like neural network is one, I don't know, SVR or SVM or something like this. Just they have every technique has a boundary, and you have uncertainties around boundaries. So if you
the thing is that what I'm describing here is for a neural network with ReLUs.
Yeah.
If I don't think that SVM can become, because what happens here is that this Y is the output of the neural network that's now encoded in these linear constraints with binaries.
Mm-hmm.
So what I'm saying here is that find the minimum distance epsilon from, so minimum distance of X, so that when I push X inside the neural network, it's going to give me a Y that's going to change the classification. Mm-hmm. And I'm able to do that because I have converted the neural network to a set of linear constraints with binaries.
Yeah.
With SVM, I don't think you can do that. Mm-hmm. And that's a problem.
Can you also comment on the output of neural networks? Is it closer to 1 or closer to 0 for the cases where it predicted as true, but, the ones that are actually true safe, but it was predicted unsafe? What was the output of neural networks for that boundary?
Intuitively, you would think that they get closer to uncertain. I mean, the closer the boundary you get, then the Y1 and Y2 get closer together, but this is not always the case. So the Y1, Y2, the difference between the two is how certain the neural network is that this is safe. But this doesn't mean that you are close to the boundary or not, right? It's two different things. Good. Shall I go on? So, as I said, this is a new research topic. Not only, I mean, for power systems, we haven't seen any other paper, to be honest, out. But also for the machine learning community is very new. And there are a lot of challenges. So one of the major challenges is tractability, as one might have expected, right? So what we have managed up to now is a 4-layer neural network with 100 nodes per layer. And in order to formulate a MIL problem that we were able to solve, we had to use weight sparsification, which means that, I don't have the neural network here, but what I'm trying to do is, so there are some routines inside TensorFlow and others that you try to put as many zeros in weights as possible and have only a few weights. So instead of having a lot of very small weights, then the neural network training procedure tries to have only a few weights and then all the other zeros. You lose a bit in accuracy, but compared to the computational performance you win, the accuracy that you lose is very small. Then also bound tightening, so because you have to tighten the bounds of all our variables, and the loop pruning, which means getting rid of activation functions, because some of the activation functions will always be 1 or 0. By 1, I mean the input column. Okay, so this is a problem, and this is a problem that requires expertise in machine learning and in optimization, because it's cross-cutting. The next challenge is up to now, what we have seen is that we have to verify or to guarantee the performance of the neural network, to guarantee the outputs, and then we have to check if these outputs correspond to the actual truth, if they are correct or not, right? So what we're trying to do right now, and we can do that for regression, to be honest, is to connect the verification with ground truth assessment and come up with a certificate. So when I train a neural network, at the same time I get certificate that the maximum violation or the maximum error of that regression is going to be so much %. It's more challenging than one would think. And then, of course, retraining is necessary, as I've said, and the quality of the training database is very important. Okay. So when we identify an adversarial example, we have to retrain to make sure that the neural network does not identify that as adversarial. Questions? Yeah.
I have one question. So can we say that, all machine learning techniques are not good for extrapolation based on Daniel's comments? Because they learn from the data that they have seen, and that is basically the big difference or the advantage of physical model or physics-based model, where they might do better in terms of extrapolation.
Before you answer that, can I
I won't answer that.
I think that I'm confused by the definition of machine learning, because I know that OLS, the traditional regression model, I think in your slides earlier, Ian, you mentioned that it was classified as a machine learning, and OLS does extrapolate. So I think it depends on where you sit in terms of your definition of machine learning. There's some interpolation machine learning models, there's some extrapolation models. These sort of more brute force type models may not necessarily extrapolate as well as the traditional statistical models.
Just want to say, as you said, they are more called statistical models. I think they existed for a longer time before even the term of machine learning exists. So that's why I'm saying machine learning. Maybe, yeah.
I wouldn't reply to that. I mean, I don't know. If I want to be careful, then but thanks a lot for the comment and for the question. Shall we move into the last, let's say, chapter topic? The last topic is physics-informed neural networks. And this is an even newer development in machine learning. The first paper of that form appeared, I think, it was published last year officially, but I think it was on archive for maybe 1.5 years. So the idea is that we exploit the physical models that we have at our disposal during the training. So just as a reminder, this is what happens with standard machine learning, traditional training of a neural network, let's say. So we just have data, and we try to fit a neural network, a decision tree, or whatever to the data. Now, the idea is that we want to exploit the physical models because all this data for power systems, for example, they follow specific models, right? They are described by specific physical models. So what made that possible is this recent development called automatic differentiation. I won't go into more details in that, but the thing is that during the training, I can calculate the derivative of an input, of the output of the neural network. During the training procedure, I can calculate the derivative of the output and measure the effect that this has on the weights. I won't go more into that in detail, but you're going to see what is the impact of that. So, and the thing is that, for example, TensorFlow already includes this kind of capabilities. Okay, this was our inspiration. And they have put some code online, and we have also put our own code online, and we're also going to share with you some code about this that you can take a look at. This is what happens. So up to now, what we had is minimization of the difference, let's say of the error, of my estimated output versus the real output. Now, what am I doing here? I'm trying to estimate the swing equation. So I have a time, let's say, from 0 to 20 seconds. I want to estimate my angle delta for a specific input of active power. So now this is my swing equation. So up to now, what I would do is I would just have time and my different deltas and minimize the distance. Now I can also include the physical model in there. So here what happens is the following, that the neural network, when it's getting trained, so what I'm trying to determine during the training is the weights W and also the biases B, right? And I take as an output the estimated delta. But now what I can do during the training is I can calculate the derivative, the first derivative and the second derivative. And then I can include my physical model, so the swing equation here, and I can drive that to 0, because this equation here, the way that is formulated, this must be equal to 0. So if I minimize this, that's why it's the square, then I actually make deltas fit into my physical model. And these are some results. So this is for two different power outputs or power generations. And you see that the exact and the predicted fit very well. Yeah, not everything is so ideal as it looks, because we're going to talk about challenges as well. But the potential is good, and I'm going to talk a bit about this first. So the idea behind that, or the cool thing behind that, is that maybe at some point these physics-informed neural networks can replace solvers of differential algebraic equations. If I train a neural network to do the job of my of a differential algebraic solver, then I can use this in real time to solve something extremely fast. In our simple example with this swing equation, which in any way is solved quite fast, the neural network could do that 87 times faster. Okay? And the reason for that is the following: that when I use a solver, I have to integrate from time equals 0 up to the time that I really want to estimate how much my angle is. So for time equal to 10 seconds, I have to perform the integration in order to reach this point. With a neural network, I can directly enter, so what is the delta time equal 10? It's going to give me the output. There's no need to integrate over the whole period. There are challenges. There are still challenges. Okay? This doesn't need, if you think about it, this doesn't need any training data, or you only need training data about the boundary conditions. So for time equals 0, you need to have the training data there. So this external data. All the rest of the data are being generated during the training, but you still need a lot of data. But the thing is, all these data are dependent on the model, so you don't need to have any historical data or whatever, as long as you want to fit that. You can use that to replace a differential algebraic solver, but you can use it also for state estimation, for system identification, for many other things, right? It's really very powerful to include the equations inside the training procedure. It's still at the very initial development. You're going to see from the code that there are still challenges that need to be solved. There are some solutions for some of them, but there's still a lot of work to be done, both for that and for the verification and for the data generation. Okay. This is the takeaway wrap-up of all the things that we discussed today. And these are the highlights. And this is some references. One of what I want to focus here is there's also physics informed for OPF. Okay. Although the authors do not call it physics informed, the way I would explain what Pascal did is that they included all these powerful equations and the Lagrangian multipliers inside the training procedure of deep neural network. So we can not only do dynamics, but we can also do optimization, we can also do other things.